All right, welcome folks to our special live stream broadcast with Dr. Mike Poland. If folks on the live chat can let me know if they can see and hear me okay, that'd be a good way to get things started. And then we'll jump right to Mike here in a few minutes and have him share some information on Yellowstone, ask him a few questions. If you have questions for Mike, you want to put those in the live chat. We've got Susan and Amanda Joe moderating there, and they can aggregate those questions and get those sent to me. That would be great. So folks can let me know, just looking for the confirmation on the live chat that we're all good to go. Okay, 5x5, good to hear. So awesome. Well, Mike, this is a treat, and I actually counted this. This is the fourth time you've joined us, so this is you've set the record, although it wasn't much of a record anyway. But I know you're one of my favorites. I know you're a lot of the viewers' favorites. So I just appreciate you taking time again to join us today.
Thanks very much. That's really fun to hear.
Yeah, so this is our fourth, and I think it's all been, maybe the first one wasn't a live stream because we talked more about your background and that, but mostly live stream. So that's great, and I know it's a fun way for folks to interact with you. So thanks for making time today.
My pleasure.
Awesome. Well, let's just get started with maybe, since you've obviously been focusing on what's been happening in Yellowstone, and we had the hydrothermal explosion at Biscuit Basin last summer. So if you want to maybe get the viewers up to date on what has been going on there with the geothermal activity and just your monitoring efforts there.
Sure. It's been a good season out at Biscuit. So in May, we put in a webcam, and that is sort of storing an image every 15 minutes. We're not streaming the video. It's iffy.
So it just takes a still, like a photo every 15 minutes.
Yeah, okay. And it stores the video on site. And so what we do is we look at the stills, and we can see whether or not there's obvious changes. We can also see from other monitoring data whether or not something happened. And if there is something that happened, then what we can do is go in and download the video that is recorded on site and then look at it and see whether or not there are any changes. And sure enough, within a week and a half after we put this in mid-May, there was a clear, every 15 minutes you get these images. There was one where it looked normal, and then the next one, there were some rocks that had moved. The shoreline was wet, change. And so when we downloaded the video for that 15-minute period, sure enough, we saw there was an eruption from Black Diamond. It went up, I don't know, 20, 30 feet or so.
So much smaller than the initial one.
Yeah.
Okay.
Nothing anywhere close to that initial one. And since then, we've seen maybe 3 or 4 more events like that. There's a temperature sensor in the pool that the Park Service is operating. And now that we know what those events look like, we can sort of associate them with the temperature record and then look back. And it looks like from the temperature record, these sort of eruptions have been occurring randomly ever since the big explosion in July of 2024, maybe occurring every 4 days to several weeks. There's no set time interval. There doesn't appear to be any precursory activity.
Right. There's kind of a range of the recurrence interval there.
Yeah. And then just in the end of July, early August, we installed a full-blown hydrothermal monitoring station just a couple hundred feet away from Black Diamond Pool. And that has a GPS sensor to look at how the ground moves, a broadband seismometer to look at ground shaking, and it has a 3-element microphone array. And that array is designed to look at very low frequency acoustic signals, sort of below the level of human hearing, but something that's very commonly made with geyser eruptions, volcanic eruptions, meteors entering the atmosphere.
This is what we call infrasound, right?
Yes, exactly. Okay. Yeah. So we have an infrasound station there now. And for the last month, it's been sending data in. And we can see there's a lot of noise coming from Black Diamond or that area. We know the directionality of the noise. We can't pinpoint the location because we only have the one station, but we can tell there's noise coming from that area. And some of that noise is associated with small eruptions. And some of them are really small eruptions, like, water goes up 2-3 feet. Mm-hmm. Other times it's almost like there's a seiche on the pool, which is sort of like just some very light changes in kind of waves, almost like windblown waves or surf. The pool is generally really, really quiet and still. And then every now and then you'll just sort of see a little wave come across the lake, and that's associated with some noise. And
so it's when you say noise, like acoustic noise,
an acoustic noise,
not,
a low frequency,
not vibrational ground.
Right.
Okay.
Yeah. So it appears that there's probably some stuff happening beneath the pool that is generating noise, generating seismic energy as well, but it's not having much of a manifestation at the surface. So there's a really broad range of things happening there. And we're really just starting to open the door on that. But it's all this new monitoring that's really making that possible.
So I got a couple questions. So the events in July 2024, the way I've always understood and explained these hydrothermal eruptions, at least one mechanism is you're precipitating mineral material along the conduits, and so that can constrict until you eventually are building that the gases, the steam, and maybe the gases behind that, until basically you get an explosion that kind of reams out and rips open that new, and so is that pretty accurate? And now we're kind of looking at, so now you don't know really what the plumbing system is. So do you think it's still reaming out the plumbing system and they're still like clogged, mineralized conduits?
That or just some of the plumbing just got really messed up by that big explosion, right? Things collapsed. There may be new pathways opening and closing constantly. So yeah, the big events are driven by just that precipitation of minerals that sort of neck down the plumbing system. If anybody has experience in an old house, like with old copper pipes,
right?
I mean, I understand this
because I live in an old house.
Yes, yes. You cut those copper pipes, you look into them, and the copper pipe might be this big around, but when you look on the inside, it's that big around on the inside, right, because of all the minerals that are precipitated into it. Yeah. And so that's sort of what's happening all the time beneath these Yellowstone hydrothermal systems. And so every once in a while, things clog up and stuff has to find a new way out. And if it's really sealed in, then pressure will build, and you get this sort of, the building of pressure allows water to exist boiling, but without becoming steam because of the pressure.
Right.
And then as soon as you make some cracks and lower the pressure, then water flashes to steam, and it sort of becomes a runaway process.
Right.
And that's how some of these really big hydrothermal explosions can occur too.
Can you get a sense of how deep? I always sort of envision the clogged plumbing system or the conduits being fairly close to the surface. I don't know why in my brain that kind of works, but can you tell where the energy in the system is coming from, if it's kind of like, a few 10 feet down versus like maybe 100 feet down?
Well, we know from the rocks that came out that it was in the upper 100 feet or so, because we didn't see any of the basement rock. All the stuff that came out was sort of sedimentary or glacial debris.
Right.
None of the rhyolite bedrock made it out. So we know that, the cap there is 150 feet or so of this debris. It didn't get below that. So it's got to be rooted in that upper part. My guess would be even shallower, because, the deeper you get, the harder it is to actually create a big explosion at the surface. You sort of have to start at the top and then dig your way down.
Right.
And that's probably why, when this eruption started, it was smallish, it was sending stuff up 30, 40, 50 feet. And then it really, after playing like that for, several seconds, then it got big. So it sort of worked its way down into a bigger reservoir of boiling water that when it flashed to steam could really drive something pretty high.
Is there a depth at which you can't get that superheated explosion happening? Like the physics just don't allow that to make it to the surface? Or does it kind of depend on lots of variables?
It's all going to be pressure temperature conditions, and offhand I couldn't say, but that's going to vary from place to place, and that's why it sort of starts at the top and reams its way back in, because once you start releasing the pressure at the top, then that has kind of a runaway effect, and you can draw in more stuff into the explosion from deeper levels because you're depressuring that as you go.
Right. So what do you think, what does this look like moving forward? I mean, it sounds like we're kind of in the unknown. We're like, we had a sort of vent clearing hydrothermal explosion. We don't know what the conduit system really looks like. Can you do borehole video? Does that work in this system, or is it too hot and too tough on the equipment? Or
well, for this one, it's probably not going to work very well, only because cameras have been put down Old Faithful, for example.
Yeah. And it's been they've mapped out the conduits of Old Faithful pretty detailed. Yeah. Yeah.
I mean, that one is great. And there have been cameras that have been put into other hot spring pools from time to time, which are mostly open pools. The problem with Black Diamond is that it is a muddy, mucky mess. So it's not one of these beautiful blue water pools where you can see the bottom. It is just it's murky.
Is that because
So I
it
don't know
has
that we,
more sulfur, like hydrogen sulfide and things that are dissolving and making more clay, like the mud pots, or is it chemistry of
it's
the
just,
water?
it's getting stirred up constantly. And there's just a lot of debris in that system. So it just seems to be kind of like nothing ever really has a chance to settle out in this pool. And that may be, one of the things that we're not seeing explosions or eruptions from this pool, but we can hear and sense seismically that things are happening. It may just be that it's sort of a constant churn.
Yeah.
And that sort of keeps it mucky.
So is this kind of uncharted waters for you guys in terms of like this could either get quiet and kind of calm and still? I mean, what are the possible scenarios might play out moving forward?
Well, we've got history we can look back on. And for this pool in particular, it has a history of having these small eruptions. And there's back in the 2000s to mid 2010s, there were, in some cases, dozens of these things per year. Then it calmed down and it was quiet until 2024. So it had about a 10-year period where it didn't do anything at all.
Right.
So it seems to be the nature of this pool to just have kind of randomish eruptions, dirty eruptions, that are a consequence of a weird plumbing system that we really don't understand. It's isolated though, because there are features right nearby that have not responded at all. Like Sapphire Pool is this famous, gorgeous blue pool. Jewel Geyser nearby is a geyser that goes off every 5 minutes or so. And those haven't changed in the slightest.
So
and they're
totally different plumbing systems, perhaps.
Yeah.
Like it's unrelated.
Yeah. So whatever happened just happened here. It only affected this pool. The other pools, the other geysers nearby, completely unaffected. So it's really restricted to this plumbing system.
So that's kind of surprising because if it's all, the shallow levels, you have this sedimentary basin fill, glacier deposits, things like that. I would assume there's good porosity and permeability in those sediments. Or do you get that mineral coating? The coating along the conduits kind of isolates it and keeps those two systems separate?
That's probably what's going on, is that there is so much silica deposition that you can separate these things out to a great degree. There probably have some connection in the more porous areas down below, but all of that hot water, as it comes through the rhyolite, it is leaching silica out of that and then dropping it near the surface. And so you get these very isolated systems.
Yeah, so they're probably connected at depth from the heat source, and the chemistry of the water is probably similar, but as you get closer to the surface, what's actually feeding the springs or the geysers or the vents is somewhat isolated with that mineral deposition.
Yeah, once you get up to the top, unless you've got a bunch of features that are in really close proximity, and there's places like that, right? Like especially if you go to Geyser Hill near Old Faithful, there's groups of things that clearly interact with one another. But then you get these isolated ones. Old Faithful is an example of one that's completely isolated, and it kind of behaves independently of everything else around it.
On its own cycle and system, and interesting. Huh. Okay, so the area is still closed to visitors. I'm assuming that whole basin. That's a biscuit basin, correct?
Yeah, the boardwalk is still destroyed.
Right. Waiting to see if there's another one before you fix it, right?
Yeah, that would have to be fixed. But there's a lot of discussion within the park now about, well, if this area were to be reopened, what would that look like? And maybe that involves moving the boardwalk away from Black Diamond Pool. Yeah. So that you're no longer near this pool that has a history of erupting. Now, not necessarily exploding like it did in July of 24, but certainly eruptions. And so, if that area is to be reopened, it might be that boardwalk just has to move away from the pool.
And what was the magnitude of that July eruption? Was that kind of a once in 100 year kind of recurrence interval magnitude, once in 10? Like how often would that occur on average?
Probably it's in the order of once every few decades.
Okay. It's
difficult to say because we don't know the sizes of some of the events that happen in the backcountry or in winters. We just don't have the observations. It might have been one of the largest events in the front country, certainly since the 1880s, which is when Excelsior had some really large hydrothermal explosions. But it's very likely that there's some stuff in the backcountry that just was never witnessed. And because we don't have, especially the acoustic monitoring being widespread throughout the region, we don't hear things that are happening in the backcountry or in the winter or at night that places just aren't
Yeah.
people aren't there to see them.
We just don't have the data, and we probably can't even go that far back. Imagine even at a given basin with the monitoring equipment, if you want to go back not just decades but centuries. You know, you see rocks on the ground and maybe you can date those, but like it's hard to get the data for multiple. If you wanted to have 20 eruptive events, I don't know if you get that much data.
Yeah, and there's a question when you come upon a pool that looks new or a crater, how did it form? Was it a single event? Was it multiple small events? And I think we have an example of that occurring just at Norris Geyser Basin in the past year. This spring, the Yellowstone Geology group was out mapping, and they found a new sort of blue water pool at Norris Geyser Basin, about 12 feet across or so. And there was clearly a bunch of debris around the pool. So it had thrown things out. So there was some sort of explosive component to this. We looked at the satellite imagery, and it looked like it formed somewhat gradually. We could see that sometime in late December, a depression formed, and then subsequent to that, it filled with water. And then in looking at the acoustic data we have at Norris, we saw some very weak acoustic energy coming from that direction on several different days. So it seems like that particular feature, which is a nice hole, it's a beautiful blue water pool, probably formed in a series of smaller events.
You could kind of piece together the evolution or the origin, if you will, of that pool.
Yeah, and all of these sorts of pools and explosion craters can be different, right? I mean, it's not that there's a single style of how these things form one big explosion. And that's the challenge we have, I think, when we just come upon one without any monitoring data to really suggest what happened. We don't know whether it was multiple small events, one huge event, what drove it.
Yeah, well, maybe one more question on, because I'm just in a hydrothermal state of mind right now. So how long-lived can some of these hydrothermal systems be at Yellowstone? I mean, we know the last big caldera-forming eruptions 630,000 years ago, and we can see the modern landscape. But when you go to Old Faithful or Norris Geyser Basin, how long-lived are some of those hydrothermal features? Are they pretty transient?
That's a good question. So hydrothermal features themselves, yes, they are pretty transient. We don't know how old most of these things are, like geyser cones, because we have a very hard time dating the material in the geyser cone. There's just not a lot of material that we can use for dating. There's some work on that's ongoing, trying to really uncover this, but it's not straightforward. We know all the geyser cones have to be at least post-glacial because the glaciers would have wiped everything out.
That's true, right.
We know that many of the areas were active when they were covered in glaciers because there are hydrothermally cemented glacial deposits. So we know that these are features called kames. I'm not a glacial guy, so this was sort of, I had to learn about this. These kames are basically piles of rock that sort of form in the midst of a glacier, where the glacier is thin or melting a bit. And Yellowstone has a specific type of kame, a thermal kame, that is kind of cemented by hydrothermal minerals. So you've got kind of a glacier covering a thermal area. It's warm, it's thinner there, the glacier's thinner there, rock and other debris accumulates there. You get this pile of positive relief. It sort of turns into a hill in this otherwise glacially scoured area. And then because you have all this hot water moving around carrying minerals, it cements that together.
Yeah.
And there are these thermal kames in many places around Yellowstone.
What's an example one? I've never seen one at Yellowstone.
My favorite is the Ragged Hills in Norris. So if you go to Norris Geyser Basin and you're walking around Porcelain or Back Basin, if you look off to the west, there's a series of hills before you get into the mountains of the Gallatin Range. And that series of hills, which is in the basin, it's right in the middle of Norris, that's the Ragged Hills. And if you were allowed to go out there, it's in a closed area because getting there is pretty treacherous.
Right.
It's a pile of junk.
Like a breccia.
It's debris.
Yeah.
But it's stuck together. It's stuck together by all this silica and other hydrothermal material that was circulating through it and then cemented it together. I believe Twin Buttes in the lower geyser basin is a thermal kame. I think Capitol Hill in the Travertine area of Mammoth Hot Springs is a thermal kame. So they're scattered around.
Right.
Porcupine Hills might be. I'm not sure about that one, but anyway, they're all through the thermal areas.
Oh,
and we know thermal activity had been going back as far as I think about 400,000 years. that's the oldest travertine deposit that we've been able to date.
Right.
And that's up by, it's Terrace Mountain.
Terrace Mountain. Yeah, I've seen that. And the big landslide there. Right. Yeah.
Yeah, exactly.
Right.
So that's the oldest.
That's sort of the
old,
that's the ancient Mammoth Hot Springs.
Exactly.
And this Ragged Hills area sounds like it's the old Norse Geyser Basin. There was something in that area, whether you want to call it Norse or not, but yeah, there's a long-lived history of that type of thing.
There was thermal activity there while the glaciation was happening. What that thermal activity looked like, we can't say. I mean, all of the geyser cones and features would have just been wiped clean, but the area was still hot, and there was still a lot of hot water coming out there.
Right. Interesting. Anything else from Yellowstone before we maybe switch topics a little bit? I mean, I'm sure you've been focused on that area, and there's all the other things happening in Yellowstone. I'm not trying to skip over those, but any other highlights from your summer, spring's work?
The cool stuff that's been going on there has really been like in the installation of the new site, and then in some upgrades that have been happening throughout the park. The modern seismic networks, if you were to put in a seismic network now, you would be using all digital broadband, top-notch sensors. But for some of these seismic networks that have been around for a long time, when they were built in the 70s, 80s, 90s, they had to use maybe analog sensors, short period, which means they don't record a really wide range of shaking. They really record just high frequency shaking. And so, that's the way the Yellowstone Seismic Network looked like. It started out as a short period network. And so part of the process of upgrading the network has been to replace some of these sensors with modern digital broadband sensors. And we're getting a few a year, trying to get down. We had 15, I think, short period sensors a few years ago. We're down to like 7 or 8, I think. So we did, I think, 3 or 4 upgrades this year. And then we installed the new site at Biscuit Basin. And we also installed a new site in the northeast part of the park near Slough Creek. So it's been a pretty busy summer for the geophysical monitoring, and I think pretty successful. It's pretty fun to see the network evolving,
right,
and being upgraded. When
you replaced and put in the more modern sensors, do you notice a drastic uptick in just total number of earthquakes? Like, wow, now we're detecting more earthquakes, or you're detecting maybe a different kind of earthquake?
It does give us the sensitivity to detect different types of earthquakes, and also to detect different types of energy. So, for example, distant earthquakes. When they come across a network, they tend to be very low frequency events, and they may not be picked up as well by the short period sensors, the old analog sensors, whereas the digital broadband ones are more likely to record this sort of very subtle and long period shaking that's caused by distant things. They're also much better for probing the subsurface. So when you've got these digital sensors that can record a range of frequencies, you can more effectively look at seismic wave speeds in the subsurface. And there's all different types of tomography. That's what this is called, right? Looking at seismic wave speeds beneath the surface. There's all types of tomography that use different frequencies of energy to get at what the subsurface looks like. And so having more and more of these digital sensors can help resolve more and more of these signals and get at what's going on beneath the surface.
Yeah, well, that's got to be great, because that's just giving you it's more data, it's more information, which is always what you're after, right?
Yeah, I tend to think of this as sort of like digital camera technology. I mean, 20 years ago, I was like, wow, a 1 megapixel camera, this is incredible. And now we all carry 20 megapixel cameras in our pockets, right?
Crazy.
The evolution,
it's just resolution,
yeah, exactly. And so the upgrades here just give us more resolution into the shaking processes that are occurring in Yellowstone, whether it's caused by a distant earthquake, a local earthquake.
Right.
We can record seismic energy from ocean waves. And in fact, that's used very effectively to look at very subtle changes in what might be going on in the subsurface. And studies using this have been going on at volcanoes worldwide.
So you mean like ocean waves crashing on the shore in the beach in Oregon, that energy is transmitted through the beach sand into the rocks, across the Cascade, and all ends up in Yellowstone, and you can detect that energy? That's
it's not, you don't want to think of it like a single wave crash or anything like that. It's sort of like the noise of the oceans.
Right.
Because there's all that water moving around and crashing on shorelines everywhere. And that creates kind of like a background hum. And that's detectable at a seismic station far inland.
Wow.
And changes in how that hum is recorded can occur due to changes in the subsurface. So let's say, for example, a whole bunch of magma starts to accumulate, or a whole bunch of cracks start to form because maybe there's a pressurization and the ground starts to crack, and so it can't as effectively transmit seismic energy. The characteristics of that background hum will change because the subsurface is changing.
Right. You've changed the medium that energy is moving through.
Exactly. Right. So by measuring the characteristics of that hum and looking at how the hum changes between pairs of sites that are located near one another, for example, you can get a sense of what's happening in the shallow subsurface. And then this is used as a volcano monitoring technique at a lot of volcanoes right now.
That is interesting. This is why we have you on as often as we can. We learn so much. So, well, let's talk a little bit more about earthquakes. So one question I kind of get, and that's why I bring Mike on to get the expert here, is like with the USGS earthquakes that get compiled on the database. Lots of people track those. Lots of people get the earthquake notification emails. I'm one of those people too. And there's been some discussion that I've heard about how earthquakes are located by the USGS, like what a locatable earthquake is. So maybe talk us through the science of that, like how the USGS locates an earthquake.
So we'll start out and say that it's not just the USGS locating earthquakes. And this is something I think is a broad misconception that, we're locating every earthquake in the country. No, and we couldn't. I mean, there's way too many. Most of the seismic networks in the country are operated locally. So for example, the Yellowstone Seismic Network is operated by the University of Utah. They also operate Utah Seismic Network. A seismic network is in Nevada is operated by the Nevada Seismological Laboratory at the University of Nevada, Reno. Most of the seismic stations in the Pacific Northwest are operated out of the University of Washington. And all of these networks do the location of the small earthquakes and then feed that information to the national catalog. So in many cases,
they're just sharing their data. Like we detected an earthquake, we've located an earthquake, and now we're sharing that with this larger repository.
Right.
Okay.
Now there is a National Earthquake Information Center in Golden, Colorado that the USGS operates. They're responsible for looking at larger earthquakes that may span networks and be picked up, in very, very broad areas, and also resolving discrepancies. So what happens if an earthquake occurs on the boundary between, say, the Nevada network and the Utah network, right? Because each network might come up with a location and a magnitude, but because the stations that they're using might be somewhat different, you'd get a slightly different result. It's a bit like thinking about maybe you're in a house and someone is yelling from another room. And if you're pretty far away, you may not know exactly what room that person's in. So you want to talk to somebody, like maybe there's somebody who's closer. Or maybe you get multiple people saying, okay, well, I heard the person yelling and it was really loud. Well, I heard it was really quiet,
Right.
and use that to try to get the best location possible. But then the USGS does do location work of some of the larger earthquakes. So mostly magnitude 5, 6 above, to try to get solutions that span broad areas and that also use different techniques for locating the events. You use different techniques for locating a very small earthquake versus a larger one.
And then maybe speak to, so that kind of covers like, our country's earthquakes. We have different seismic networks that operate in a region. They share to a US or a national database. But then if there's an earthquake like we had one in Afghanistan this last week.
Right.
And in Turkey, we only detect those quakes that are above a certain magnitude, right? If there's a 2.3 in Greece, the US networks are never going to know that earthquake existed. But we can detect, like usually I think on the website, it's like 4.5 or so and above. So how is it different when you go outside the US?
So every country or many countries have their own seismic networks. And those data sets are not necessarily shared with everyone else in the world. And so, occasionally I'll see questions that are, like, well, how come these very small earthquakes in wherever, Morocco, aren't appearing on the USGS map? Well, we don't have access to any of the data that would allow anyone to locate those events. That's happening there. So if you want to know about small earthquakes in Morocco, go to a website for the Morocco seismic, like someone operating a seismic network there, right? That's not the USGS, that's the United States Geological Survey. in terms of the larger earthquakes, we do get data from the International Seismic Network. There's sort of an array of seismometers around the world that are publicly available, and that can be used to locate some of the larger events. And the way seismic energy travels for a larger event, it can actually be much more advantageous to use stations farther away to locate the event than stations very close. Like, I mean, if there's a magnitude 1, you want your seismometers right next to it.
Yeah.
If there's a magnitude 6, the seismometer right next to it's going to go off the scale.
It just gets overwhelmed, right? Yeah.
Right. So it's very difficult to get a good magnitude and location when you're that close in. So you would tend to use these international network of stations, the global seismic network stations, to locate and determine magnitudes on some of these larger events. And that takes a bit more time, and there are different types of magnitude scales. You know, the Richter scale is what we say in sort of a generic way, but there are different ways of measuring magnitudes and different scales that are used that are subtly vary from one scale to another, and they measure slightly different things. So it can be a complex process to get a magnitude for a big earthquake. And of course, you want to get that magnitude out quickly and the location out quickly, because that can help direct emergency services. Mm-hmm. Or if it's happening offshore, it can really tell you something about whether or not a tsunami is likely to be generated. So there's a tremendous emphasis put on getting locations and magnitudes for large earthquakes out, you know, as quick as you can. And it might be a rough estimate.
Right.
But you need that rough estimate in order to know, like, all right, is this something that we need to worry about in terms of tsunami or damage or whatnot? And the refinement can happen later.
Yeah.
Sometimes minutes, sometimes occasionally it takes. Yeah. So the emphasis is on speed in getting out something that's actionable, and then the refinement can happen a little later on.
Okay, so that kind of brings me to the next question that I often hear is sometimes you'll see an earthquake, and I've seen this. Initial earthquake magnitude comes out, and I think everything's automated, right? The computers are detecting the P waves, the S waves. They're doing the triangulation, figuring out where the epicenter is in 3 dimensions, estimating the magnitude, and sometimes even tell my students, I hope this is correct, that if it's a big enough earthquake, the earthquake might still be shaking. Like there might still be energy from that earthquake, and we already have a location and a preliminary magnitude. But sometimes you see USGS, and I'm sure other agencies as well, put out that magnitude, and then it gets revised. Mm-hmm. Sometimes it even gets revised maybe a 3rd time or a 4th time. So what actually what's the behind the scenes explanation for what's happening there when magnitudes are adjusted?
So you'll often see on those messages that come out, it'll say like, updated, level or it'll say like this is an automatically generated location and magnitude. It has not been reviewed by a seismologist. That's the computer saying, all right, something happened, and I am going to pick the timing that I think is the start time for the earthquake. It's one of the more important aspects of understanding where it is. And then depending on the type of magnitude you're using, it might be the duration of shaking of a certain magnitude. It might be the maximum amplitude of the shaking on a seismometer. And so the computer is doing all of that very, very quickly, and then shooting its magnitude out to say, hey, network operators, 24/7, duty scientist. I think there was a magnitude 2.5 in wherever. And that, even if it happens in the middle of the night, every seismic network typically has a person who is responsible 24/7. Now, that doesn't mean they're sitting there staring at the screen, looking at the wiggles. Right. They may be asleep, but they'll get that call saying a noteworthy earthquake has occurred, I think, the computer thinks. You need to check this. And so then, the seismic analyst will get up and, load the earthquake into their computer screen and do the picks themselves.
So they're verifying that the earthquake actually happened based on the seismic data, and then they're double checking magnitude, location, and some depth, some of those things.
Exactly. And you can imagine that, the computer only kind of knows, all right, shaking has occurred. and it will pick a start time for the shaking that may not be right. Now, a human analyst might know, for example, this particular station has a lot of background noise because it's close to a road, or
soft
it's
rocks,
just
something, yeah.
Yeah, I mean, or maybe it was really windy that day and there's a little bit of wind noise or whatever, right? I mean, the seismic analyst will typically know the ins and outs of the stations in their network, and they can say, well, I think this pick is not very good on this station, and I'm going to pick, do the pick that I know is better, or I'm going to throw this station out and not have it be part of the solution. Or it's going to know that, well, the pick for the magnitude of the earthquake based on this station is really not very reliable because this station has some bad character, whatever, right? They know that network. And so they will provide a much more accurate location and magnitude. The locations typically are pretty good from the automatic picker, but the magnitudes often need a bit of work, and there's different ways of calculating magnitude, and you may vary the technique you use depending on the characteristics of the earthquake. So that one takes more refinement.
So the data that's sort of the most critical to analyze, it sounds like, if I'm reading you right, is the arrival times of those seismic waves on the seismogram. And then also, we're talking about magnitude, like the actual amplitude of the wave, how you either measure that or assess that. How do they figure out the beach balls, the moment tensor solutions? Like, is that coming from that same bit of data, or that's how that first P wave moves, right? Whether it's compressional or tensional, and then looking in the area, the map.
Yeah. So the beach balls, the focal mechanisms, these moment tensors, are recorded by when you get a very clear first motion at a site. Is it up or down? And you can then plot that on sort of a map of where the stations are.
And really in 3D, right? It's not just a map, it's three-dimensional.
Exactly. Yeah, it's sort of a hemisphere, right, that you're plotting this on. And based on the distribution of whether or not the first motion was up or down, you can sort of figure out the orientation of the fault plane, or at least get some constraints on that. And so, for example, if there's an earthquake in Nevada, then it's very likely that the fault plane is roughly north-south. All the faults in Nevada are roughly north-south, most of them. And so you can get a sense of, all right, well, it looks like this fault was a north-south fault. It's located on this side of a basin, and so it must have been this basin-bounding fault that ruptured, and it was a normal faulting event, so it was sort of a tensional earthquake. You can get all that information from the beach balls. But that means you've got to have high-quality first motion recordings on enough seismic stations that you can actually map that out.
Yeah.
And so if you only record it on 2, 3, 4 stations, you're not going to get that. You need to record it on a whole bunch of stations. The more stations you record it on, the better your focal mechanism will be.
Is that why I don't see, I look at the earthquakes enough, and for for big earthquakes, you always get the beach ball, right? Because it's felt by so many stations, but you can get to a certain magnitude and you just don't see the beach balls because the either density of the data is not there in terms of stations close to that, and the energy of that isn't traveling far enough to enough stations that we just can't put that together.
Exactly right. So there's a magnitude 1.5. Even in a place like Yellowstone, where you have a really big seismic network, depending on where it happens, it may not be recorded by enough stations, or clearly recorded, to know what that first motion is, to be able to reliably make one of those focal mechanisms. So you typically don't see them for the really small earthquakes.
Interesting. Yeah. So, but the arrival time data and assessing the magnitude, those are kind of the most critical things that the seismologist is going to be looking at specifically, and making sure the computer's choices of where that data begins or ends.
Right. Yeah. And so you can imagine there's levels of this that happen. Like the first level, okay, the earthquake happens and the computer makes its pick. And if it is something that's the computer thinks, hey, this is, magnitude 2 range, it'll send out a note. And if there's already, if it's, normal working hours, then there's probably someone sitting right there. They'll do a check really quick. If it happens in the middle of the night on a weekend, it's going to call someone, wake them up. The response time is typically in the range of 5-10 minutes, which is pretty good for going from dead asleep to okay, I got this.
Yeah.
But so that's the next level, right? Okay, I've looked at the stations that I have access to. I'm going to assign this magnitude and this location based on these stations. Well, maybe subsequent to that, you've got other seismologists that say, you know what, I'm going to look at beyond the network that this earthquake occurred in. I'm going to look at a compilation of data sets from other networks. I'm going to combine a bunch of things and see if I can refine this even more. And if it's a bigger earthquake, maybe it's recorded better farther away, right? And that might not be, that first level seismic analyst solution might not be one that's looking at everything, because that takes longer, right? And in many ways, you're trying to get these things out as quickly as possible so that people know whether or not this is something that requires a response.
Right.
And so you can even see, level 2, level 3 adjustments, usually not so much to the location, but the magnitude especially, as more and more data are examined. And that's all about sort of like, look, we want to get this right.
Yeah.
And frankly, what the difference between a 4.9 and a 5.1 is not huge. I mean,
but it's the protocol they use, and it is
right.
more important for the bigger earthquakes, like a 7.4, 7.7, like that's pretty big. That could mean, like in terms, like you said, like search and rescue or tsunami generation, that could be. So it's the same protocol regardless of size. Yeah.
And when you get those really big earthquakes, then, you may get the better recordings of those earthquakes on the other side of the planet. And so then it really takes a while. And also, every seismometer on Earth is going to be just noisy for hours after those really big earthquakes. I mean, those big earthquakes even set off tilt alarms at the Hawaiian Volcano Observatory. Right? Because the ground is vibrating so much.
You can see it on the tilt meter readings,
Exactly. Right. So Will, I remember I was on staff at HVO in 2011 when the Tohoku earthquake in Japan happened. And suddenly we had all these tilt alarms. And I was like, that's okay. I looked at the tilt data. And as soon as I saw the tilt data, I went, there was a big earthquake somewhere.
Yeah.
Right. Because you could see every tilt meter. And then, of course, the seismic analysts at HVO were seeing the same thing on the seismometers. Right. You can see all that energy coming through. And so big earthquakes, it's actually pretty hard to get good magnitudes because the whole planet is just saturated.
It's just so noisy.
Yeah.
Interesting. Huh. Wow. Well, I hadn't really thought of it that way. So what about sometimes the other last sort of like, I don't know, like a urban legend or question about USGS earthquakes is like these unreported earthquakes, like quakes that go, I don't even know what people are asking specifically about this, but like quakes that weren't reported by the USGS. Does that just mean they're not locatable quakes, or they're not shared with them perhaps by the seismic network, or?
Well, this is a tough one, right? Because I've had people ask me like, hey, I felt something. So what, can you tell me the time and date that you felt this? Yes, I felt that it was like within a couple of minutes after noon on this date in Central Oregon.
Right.
Okay, great. Then you look at the seismometer from Central Oregon, from, many seismometers from Central Oregon at that time, and there's nothing. It's like, well, I don't doubt that you felt something. Whatever it is you felt did not shake the ground over this broad area.
Yeah.
So,
it was, it wasn't an earthquake.
Right.
Yeah.
And that's not a very satisfying answer to some people. They say, well, no, I felt the ground shake.
Sounds like you're saying they're lying or something, right?
Yeah, I'm saying I don't doubt that you felt the ground shake. I'm just saying that it wasn't recorded seismically. So whatever it was very local.
Yeah, I mean, you just brought up something that I've dealt with here in Southern Idaho, and I've done like the local news thing. This has been for years ago, but we have these things here, and they probably have in other areas, but they're called locally here skyquakes. Have you even heard of these?
No.
So let me explain. So I've even experienced them. So you hear a rumbling sound that lasts for a few seconds. Occasionally it will vibrate your house. And people think they're earthquakes, which is very understandable. And I look at all the data, and as the local geologist, I'm like, hey, these are not earthquakes. I don't know what it is. So they've been called skyquakes. And my best explanation for them, right or wrong, is we have, maybe 70 miles as a crow flies from here, like a bombing range. And I wonder if, given certain atmospheric conditions, high pressure, calm conditions, no wind, usually it's in the evening or the morning. I have noticed that a little bit. If they're out there, on the bombing range, could those acoustic waves from the explosions transmit, 100 miles or so across the deserts of Southern Idaho and be heard and felt a little bit in your home. So maybe you can solve the mystery of the skyquakes here.
Okay,
in 1 second.
So what you need is an infrasound array.
Yes. Yeah, I guess
right.
so.
I mean, so, and this is, you put out 3 sensors. They're typically, I don't know, maybe 50, 60 feet apart, like on the triangle. You can put out more if you want.
They can be that close together?
Yeah.
Wow.
Because the speed of sound is relatively slow, right? 340 meters per second or so. And the recordings are high frequency enough that as a seismic, as an acoustic wave passes over this 3-element array, it will hit the array locations at different times.
Right?
Subtle, right? But this is why, you know, like if you're watching a baseball game in the bleachers and you see the batter make contact, and then you hear the crack a second later, right? Speed of sound. Yeah. Same principles here, only because each point in the array hears the sound at a slightly different time, you can use that to point back to the direction from which it came. So if you have one of these arrays out there and you've got one of these skyquakes and your windows shake and you're like, well, that was something, and it's not seismic, look at your acoustic array and see if you get a pressure pulse, because that's really what it is. It's an atmospheric pressure wave. Right. And then you can get the directionality.
Like
of
a 3-point problem will figure out the direction that it came from, basically.
Yeah. Yeah. So you sort of know, like, okay, it's coming from the bombing range, or it's not, you know, right? And this is basically the principle behind the reason that we know a lot about acoustic monitoring is because it was used to help monitor for nuclear tests. Right. Because if there's a big explosion, if you have acoustic arrays around the planet, multiple ones will hear the explosion, and then you can sort of triangulate the origin of the explosion. You can
figure out who's setting off nuclear devices, right?
Exactly. Yeah. Right. But guess what? They also hear volcanic eruptions. So there can be, and because this energy travels through the atmosphere very efficiently, we can hear things that are very, very far away. So acoustic sensors, like in the middle of Alaska, in the middle of the Aleutians, can basically hear eruptions from the entire chain. You know,
and they're not they're not affected by like atmospheric, like there's a tornado, there's a hurricane, there's high winds. It's snowing and raining hard here. Does that?
They are.
Okay.
They are, and like the wind direction matters.
Yeah.
So we typically put weather stations alongside these arrays because wind direction matters, wind speed matters. We often try to put the arrays in little clumps of trees or with a wind screen on top of them so that the wind energy that's coming through is sort of buffeted and it's not recorded. So if there's a storm, well, and then you get one of these skyquakes, you're probably not going to record it very well. But if it happens on a nice calm day,
that's when they generally occur, like 2 or 3 I've heard or felt. So there's your next research project. So and I don't know if maybe it's just a local thing here. I don't know. I haven't like researched it to find if anyone's reported similar phenomenon anywhere else. But
well, it's if there are big enough booms, it will shake the ground. So this is a bit like thunder, right? There are thunderclaps where the ground shakes. And one of the things we do with using these in a volcano context is to look at the coincident signals we get at seismometers and acoustic sensors that are located in the same place. So we always install them together. Mm-hmm. And that can tell us something about coupling of energy. And here's another example of why locating earthquakes is hard, if we can circle back to that. We had this hydrothermal explosion that occurred at Norris Geyser Basin back in April of 2024. It created a sound that impacted the ground, and it radiated outward from the explosion site.
So the sound went into the ground. The sound of the surface went into the ground. Okay.
Exactly. So we recorded seismic energy up to almost 10 miles away from the explosion site, but it was traveling at the speed of sound. Now, a seismic wave travels at kilometers per second. An acoustic wave travels at hundreds of meters per second. So the acoustic punch to the ground was recorded by the seismometer that was 10 miles away, like, tens of seconds after the event.
Right.
If it had been an earthquake, it would have been recorded
almost instantly. Yeah.
Yeah, like a second later, probably less. And then this is a problem for the computer, right? The computer expects to see a whole bunch of seismic energy that's recorded by seismic networks basically within a, plus or minus a few tenths of a second. This event that occurred at Norris Geyser Basin was recorded in seismometers all around the area, but not at the same time. So the computer looked at this and thought, this is nothing, right? The computer didn't identify that as an event because it wasn't a nice coherent package, right? And it took a human analyst to go, whoa, look at this. When I line up the seismometers with distance, you can see the propagation of this wave outward, and it's moving at the speed of sound. So this is, computers are great. AI is changing things, but it's even in AI, it is still artificial intelligence.
Right. Human brain hasn't been replaced just yet.
Not yet. We got another year or two at least.
Yeah, at least. So, well, cool. Let's, if it sounds good to you, Mike, let's go to maybe some viewer questions. I don't want to hog all our time. I feel like I've done that a little bit already. So let me pull up the first bit of questions here from a minute ago. And thanks everyone for joining us. Hopefully this has been helpful. I just love learning, so it's just great to talk to Mike and pick his brain a little bit. So, okay, waiting for the questions to pop up. Skyquakes, that's a new one for you, huh?
It is. I have heard various people talk about booms.
Yeah.
And I don't doubt that that's true. I've heard things. I was like, well, what was that? It could have been I live not too far from a rail yard.
Right.
So sometimes I think it's trains hooking up, or could be a sonic boom, or but I'll even look occasionally like at a seismometer that's nearby. Like, it didn't record anything, so whatever it was.
Yeah, I mean that's my best hypothesis until but it could be it could be a sonic boom too. They could be out there breaking the speed of sound. I grew up on Air Force bases, so I think I know what that sort of feels and sounds like, but could be potentially. So okay, here's an anonymous question. Can you predict eruptions, explosions from the geysers and hot springs like at Biscuit Basin?
God, I wish. This to me is this is a really big goal. So can we predict them? No, right now, no.
Right.
We can start to detect them mostly through their acoustic energy, but what's happening is happening so fast that it's difficult to predict. So for example,
sorry to interrupt, you're only when you say you can detect it, basically, one has begun because you're seeing signals, but beforehand, you're not seeing anything. There's no way to forecast it okay.
Now, part of the challenge is that you'd want to have a whole bunch of monitoring equipment in place where one of these was happening to know if there's a signal, right? That's out there to detect. Maybe, for example, before one of these events happens, there is an accumulation of water vapor, say, or there's more boiling water. There's some change like that in the subsurface, and that might manifest in, I don't know, some change in the electromagnetic structure of the area. The only way you'd know that is if you had an electromagnetic sensor running in the right place at the right time. That monitoring is not cheap and difficult to do, difficult to maintain, and we don't know where the explosions are going to happen. So you could sort of put one out at your sort of favorite area.
How many hydrothermal features do you have in Yellowstone? Thousands, yeah.
And 10,000?
Oh.
Yeah. I mean, you could put one, it feels like it could be a Bugs Bunny cartoon, right? But you'd set it up over here and then you get an explosion there. So you run over there and then you get an explosion over here. Yeah. So we don't know. I would like to think that there is some signal out there that if we had the right monitoring in the right place, we could say, you know what? There is a characteristic signature that one of these events is going to happen, and we can use that as a monitoring and early warning tool.
Right.
We don't know if that's true or not. And the process happens so fast, right? Water flashing to steam, that's why it's so explosive. So we don't know right now if that's something that we'll be able to forecast on. But I think a large part of that's because we don't have the data to say whether or not it's there.
Yeah.
So that's a goal.
Yeah, it's a goal for now, and stay tuned.
Yeah.
Okay, I think same person, another anonymous one. How many people work on mapping and data reading at Yellowstone?
Interesting question. So all of the seismic monitoring is done by the University of Utah, and they have a team of people that works on detecting earthquakes, maintaining equipment, and so forth. I don't know the exact number offhand. It's probably on the order of a dozen or so. They also work in Utah, so they have sort of a broad area that they're responsible for tracking. There's a group called EarthScope. They do all of the maintenance and operation of GPS equipment and borehole seismometers and borehole strain meters and borehole tilt meters. And there's probably 6 people there that have a broad area of responsibility, but also work in Yellowstone. There's, for mapping, there are geologists from the Montana Bureau of Mines and Geology, the Wyoming State Geologic Survey, Montana State University, that do mapping of various kinds in the park. So that's one of the things that I think makes YVO a fun observatory, is that there is a really diverse array of people from different institutions that contribute. No one is really, well, aside from me, there aren't many people that are specifically Yellowstone is your responsibility.
Right. They're more regional based.
The seismologist at the University of Utah, Jamie Farrell, he's been working in Yellowstone most of his career and knows it like the back of his hand. And so he's really dedicated to Yellowstone, whereas many of his colleagues have responsibilities in many places. So there's only a few of us that have this as a primary responsibility, but there are dozens of people that contribute to the overall effort.
Yeah, they come and dabble in. All right, Amanda Joe wants to know, do you know if there's a comparison between the hot spring systems in Iceland and Yellowstone, or are the systems just very different?
They are probably pretty similar in a lot of respects. Now, one of the things you have in some of the systems in Iceland is a lot of rhyolite. And so you can get hot water moving through that system, just like you have in Yellowstone, dissolving silica, bringing it to the surface. So a lot of the conditions that you have in a place like Iceland, or in New Zealand, especially North Island of New Zealand, the systems are pretty similar. Right. There's a lot of similarities between what's going on in those places. Which
is interesting because they're all different plate boundaries, but I mean, they're all generating magmas at depth and heat. So that's the fundamental, like geothermally, they're similar because you just need hot water. So yeah,
hot water, you need, so you need the heat source and the water source, and
shallow water
like
table.
Iceland. Yeah, exactly. I mean, the Yellowstone is the highest area in the Rockies on average because a lot of snow. But then you also need the geology that is able to support these conduits. And so, a place like Hawaii, you've got a lot of rain, you've got heat, but the geology is not conducive to setting up these conduit systems. And so you don't have geyser or hot spring systems. There's a couple of hot seeps and so forth, but nothing like we get in these other systems.
Right. Is that because, it's mainly basalt and the hot water doesn't really dissolve out minerals as readily from the basalt and then reprecipitate them along the conduit walls? Is that pretty much? Yeah.
And the basalt just isn't really conducive to maintaining hot water reservoirs and conduit systems. It just doesn't wear away in that way, and it's so porous that water just
just goes right through it. Yeah.
Right. I mean, when it rains on Kilauea, there's no rivers on Kilauea, right? I mean, you have to go, and when it rains at the summit, it has to rain really hard to see standing water, and it doesn't stick around that long. It just right into the ground.
Super permeable. Jeffrey Porter wants to know, is it just the elevation and the amount of precipitation that accounts for Yellowstone's 300 plus or so waterfalls? And is that unique to Yellowstone? So something more on the waterfalls in Yellowstone.
That's a good question. So a lot of the waterfalls are driven by the geologic conditions, and especially some of these very resistant lava flows, which gives you a lot of big cliffs in Yellowstone, intersecting with areas that are just not nearly as resistant. So some of the places like Fairy Falls, which is a really high waterfall, that is a case of a river that's just going off the edge of a lava flow into a non-lava flow. In the Grand Canyon, the Yellowstone area, you've got some very resistant, more recent flows that are capping altered rock. And that's why the Grand Canyon of the Yellowstone has that, that gorgeous white, yellow, red. I mean, that's all altered material, altered rhyolite, and it erodes out pretty easily. And so you've got the resistant stuff meeting the less resistant, and waterfalls naturally form. So I think it's less a consequence of all of the river systems and water. I mean, you have to obviously have the water in the rivers,
Right.
and more a consequence of the really interesting geology and the juxtaposition, some of these very resistant rocks with the altered or, sedimentary deposits that erode away pretty easily.
Yeah. No, that makes sense. Yeah. Like there's hard rocks and soft rocks in Yellowstone, and then you have plenty of water.
Yeah.
This goes back to our discussion on seismic tomography. Mama Sugar wants to know, how expensive are one of those sensors? Someone's got some money to burn or something. I don't know.
I'm offhand, I can't give you the exact number for like a single seismic sensor, but I don't know, say something like 10 grand, maybe. Right. Then you also have to have a data logger that goes along with it. So just the sensor, I don't know, it's many grand, another many grand, maybe 10 or 12 for the data logger, or 8, somewhere in that neighborhood. So the package is in the neighborhood of like 15 to 20 grand or so, I think. Plus you need to have some supporting equipment, especially if you're going to build a new site. You need to have solar panels, you need to have batteries, you need to have a charge controller, you need to have lightning arrestor. There's kind of a cast of supporting equipment that goes along with it. So installing a brand new site costs, more than 20 grand. And then if you add more sensors, GPS, the cost. And
you would need an array to do it. I mean, if you just had one sensor, yeah, you're collecting data, but you're pretty limited on what you can do with it until you have an array of sensors.
Yeah, I mean, this is like back to the person that's, if you're in the same building as someone and you hear them yelling, if it's just you, all you know is that there's someone yelling in this building. Yeah. But if you have 10 people scattered around the building, then you all get together. You can probably figure out where the yelling's coming from.
Much more informative. All right, David Newton wants to know, what other background seismic signals than ocean waves crashing are useful for analysis, and how are they used?
Lightning, that's more with electromagnetics, though. There's sort of a background electrical current that can be used to measure how the electrical conductivity of the ground changes over time. So electromagnetic sensors can use sort of background global lightning. Mm-hmm. I don't think I've heard of anyone using atmospheric explosions for this sort of thing. So really there's also kind of microseismic noise generated on lakes by wind. So as wind blows across a lake, it's moving water around, and that can create microseismic signals.
Like the tides almost, maybe? Tides probably.
Kind of, yeah. Okay. Yeah, although it tends to really come and go with the winds.
Right.
So it's anything that can create that sort of low level noise that can be picked up over a broad area, because it's pretty low frequency, so it travels pretty far. But the big one is I think it's called like the oceanic microseism. And that's sort of a hum that you hear globally.
Interesting. Yeah, I hadn't even heard of that. There's a couple little things there. All right. Dan Hallett wants to know, does the USGS share their data with the international community?
Yes. All of the data that are collected by the local seismic networks are public. So for a lot of these networks, you can kind of go to the seismic network website and get, either real time or Webby quarters, or you can actually see the data. If you have some specialized viewers, which it might take a little bit of know-how to get those up and running, you can go into EarthScope. That's that group that also does the ground deformation monitoring. They also archive all of the seismic data, not just in the US, but in some other places as well. And so you can sort of tune into their feeds and display real-time seismic data for any place that they have access to. It's not as simple as just clicking on something, and usually not. Some websites do have that functionality. And I think EarthScope does have a data viewer where you can kind of click on a site and see kind of a real-time feed.
I think they do. I've played with that.
Yeah, but there's also, the USGS has some software we call Swarm. It allows you to open up kind of any seismic network that's in the US and look at data from different sites. But installing it and linking it to the right servers and so forth can be challenging. I find that I use that to look at earthquakes in Yellowstone, and every so often it sort of conks out because some server changed somewhere and I got to find the new IP address. But is
it even practical to have, would the utopian ideal be that we have like some global, I mean, you said there was kind of an international seismic thing, but if we just spaced out, seismographic stations every however often we needed to globally, and then globally shared that data, is that like too pie in the sky Pollyanna utopia, or is that feasible?
Well, it's sort of what the global seismic network is meant to be.
Okay.
It's not evenly spaced,
and
there's some places
there's got to
where
be vast regions in certain countries where like you're not getting anything in here. So
right. Yeah, and that's, there are some socio-political reasons that it's kind of hard to operate a seismometer in some places.
Yeah.
So it's and some practical logistical reasons too. So it's not. I don't think it's completely Pollyanna to think that that might be possible, but that's when you think, well, we have a hole here. We have a hole in the global network. Well, there's probably a reason that there's a hole there. It's probably really, really hard to put something there and maintain it, keep it going, keep the data flowing. And then, you do have to find agencies that are going to maintain it and fund it, keep it going. So it's not as typically it's sort of a national agency that's decided, okay, these are the gold standard sites that are going to be contributing to the global seismic network.
Yeah. Do we have underwater seismic stations? And I guess they'd have to be somewhat shallower water, but do those exist? And are those part of some networks?
I honestly don't know if there are any that are part of the global seismic network. There's probably somebody watching this right now that's like, yeah, there's one here and here. And I don't know for sure. There are some seismic sites that are underwater that are cabled to the land, and
because it's relaying the data that's the hard part, right? Like you can detect the earthquake, but how are you going to get that data out?
Right. I mean, a lot of the ocean bottom seismometers are deployed, and then they are retrieved months, a year later, and then you download the data. It's all stored on site. It's not necessarily transmitted in real time. But on axial seamount, just off the Oregon-Washington coast, that is monitored by a cabled array. And so there are seismometers and pressure sensors out there that are measuring how the ground is moving, and they're transmitting data along the cable, and then it's being processed and looked at in near real time.
Right.
So axial is underwater, 300 miles off the coast. It's better monitored than some other volcanoes on land in the world.
Right. And overhyped, would you say, in the media? At least the stories I've seen, I'm like, wait a minute, it's a divergent boundary. It's just like any other part of the mid-ocean ridge. They erupt all the time. They're under thousands of feet of water. They're non-explosive. Like they're going to have basically nil effect on humanity. So
it is kind of funny, right? I mean, how
they did make the rounds.
I'm friends with one of the guys that has worked on axial for decades, Bill Chadwick, and he gave this presentation at AGU last year, and basically it said, based on the inflation, and he's been pretty successful at forecasting axial eruptions based on how the ground's moving. Mm-hmm. Based on the inflation, it looks like it's kind of nearing that point at which we would expect an eruption would occur, perhaps sometime in the next year. Yeah, and then suddenly it was like, we chatted about it. He was like, I can't believe and it's not like it's never erupted before, right? It's like erupted in 3 times in the last few decades, and anyway, it's kind of funny to
the media kind of ran with that one.
Yeah, and it does cause legit concern for people. I had somebody write to me and say, I'm really concerned. I have a child who's going to college in somewhere on the West Coast. It wasn't even on the coast. It was sort of inland.
Yeah.
Should I be concerned about this? And I think my guess is that the reason is the Hungatonga eruption, right? That was a submarine volcano.
Right.
Now, okay, very different volcano, very close to the surface, not miles deep, and very different style of eruption.
Right.
So you can't equate those two, but I suspect that's probably what's going through some people's heads.
Connecting the dots.
Yeah. And it created a tsunami that went around the whole Pacific. So it's easy to understand why that would make people nervous.
They wanted you to quit your position at the YVO and become our axial seamount volcano observatory scientist-in-chief.
Nobody wants that. There are so many better people that have been looking at axial for a long time.
Right.
It's funny how well we know axial.
It's probably the most well-studied, documented submarine volcano. Is that pretty true? So at least one I can think of, like, or at least divergent
I
boundary.
think so.
Yeah.
I mean, we have better maps of axial in terms of the resolution of the bathymetry than we do for the topography of some volcanoes that are above water in some places. So, yeah, the effort that has gone into understanding the axial is really neat. We're learning a lot about it, and then you can use that to better understand volcanism on the seafloor in general. So it's really paying off.
Yeah, like it's. Okay, last question on this sheet here, Mike. Mama Sugar wants to know, why isn't there a single universal scale when it comes to earthquake magnitudes? So why do we have, when we look at earthquake sizes, why are there so many different methods of measure?
Well, it sort of depends on how the earthquake is recorded. You know, like one of these big global events that's recorded worldwide, you wouldn't necessarily use the duration of shaking. Right. Because it's going to be shaking forever, right? So the duration magnitude might be useless. And I think if there was a magnitude that, I will speak for my seismological colleagues. Maybe I'm speaking out of turn here.
They may not want that.
Yeah, the moment magnitude, which is sort of about the energy release, is really how we like to think of most earthquakes. Because you can compare that, you're being energy release. You can also calculate a moment magnitude from, say, ground deformation. So if we record how the ground moves using GPS, say, you can calculate an earthquake magnitude based on that as well. And oftentimes it doesn't agree with the earthquake magnitude, because that what's happening is some of the energy that's being released is not happening seismically. It's happening in how the ground is moving.
Right.
So there are so many things going on with how the ground is shaking and how it's being recorded, that it's really difficult. You know, like you wouldn't necessarily be able to calculate a moment magnitude, an energy release magnitude, for a very, very small event. You might need to use the amplitude that it's recorded at, because it's such a small event and it doesn't last very long. But that exact same way of trying to measure something doesn't work with a really big event. So it'd be nice to think like we've got this one scale. But, you know, sometimes you'll see, especially with a large earthquake, and it gets confusing. Like this earthquake was a magnitude 8.2 based on one scale, and it was a 9 based on another. And that's a huge difference. But you have to pay attention to what style of magnitude is. And often that's indicated by a little subscript, you know, the M, and then there's a W, or a D, or an L, or a, you know. Yeah,
but a lot of time when it's reported in a news or something, they might just, magnitude, they just use the word magnitude, and then you don't know, well, was it moment magnitude, was it Richter scale, was it something else? And
to an extent you're really getting into the weeds, right? Like, you know, a magnitude 8 or 9, that is a humongous earthquake. It's causing a lot of damage. It does matter whether it's an 8 or a 9, but this is where we're sort of getting into like, all right, well, let's talk about magnitude scales and exactly what's being measured. And there's some articles online that explain more about the different scales, why they differ, how they're used. There are real reasons for that. And because earthquakes, small earthquakes especially versus big earthquakes, are recorded in very different ways, you can't really apply, there's no one size fits all scale.
Yeah. You got to look at the different parameters, how deep it is, the length of the fault. There's all these different things. So
and some of it's based on how it's recorded as well. I mean, I'll leave you with one last anecdote. So when I was living in Hawaii in 2006, we had a magnitude 6.7 earthquake off the coast. It happened on a Sunday morning. I mean, it woke me up. And you saw like the house is shaking. Think like something, that was a big one.
Right.
You could tell it was a little further away because it wasn't sharp. It was more of a wave style motion. And then in looking at magnitudes, one of the networks came out with a magnitude like 4.5, something like
really
that.
Low, yeah.
And the reason was because the shaking saturated all of the local stations. And the way of calculating a magnitude was not tuned to a big event. It couldn't cope.
Right.
And so it assigned this magnitude.
It did the best it could, but it was way off. Yeah, not accurate.
Whereas I think one of the Tsunami Warning Center got a magnitude that was much closer to what it actually ended up being. Ultimately, the magnitude was calculated using recordings that were away from Hawaii.
Yeah.
And it came out with a 6.7, which was, I was like, okay,
significant.
that's what it felt like. Yeah. But what that did do is it motivated the replacement of a whole bunch of the seismometers in the network in the island of Hawaii with some of these broadband sensors that are capable of measuring a larger range of shaking.
Right. So you could better capture those quakes in the future.
Yeah, because the network was tuned to these very small earthquakes that we get in Hawaii. And in aiming at that, it became harder to measure the bigger earthquakes.
Yeah.
With that network.
It's hard to get it. You can't have it all sometimes. You want the big earthquakes.
Yeah, this is all those jokes about mechanics or something like where you can have it fast, cheap, or done well. Like pick two.
Yeah, but you can't have it all. Well, I have one more sheet. Are you okay if we do a couple more questions?
Yeah, sure.
Okay.
I'll try to
rapid fire, or do what you can with these. So
lightning round.
Well, yeah, as best you can. Foxfur wants to know, is it weird that I felt more low magnitude quakes where I live in Central and West Texas than I do here in Colorado Springs?
Not necessarily if they're happening right beneath you. Okay. So I've never felt this myself, but I've talked to people that felt like a magnitude 2, but it happened right beneath them and it almost threw them up in the air. Whereas somebody, a mile away didn't feel a thing. So your proximity matters. And so if you're right on top of where the seismic energy is originating, you'll feel it big time. And then if it's like maybe in Colorado, it's deeper, it's farther away, same earthquake, no one feels.
Right, or the types of rocks it's moving through. There's all these variables that'll influence how it's felt, right?
Yeah, absolutely. Okay. So the context really matters.
Right. All right, Susan Smart, is there more background noise at the Biscuit Basin Station than at Norris because of the increased human activity? And if so, do you see time of day differences in the background?
Very good question. And the answer is yes. We hear a lot more noise during the day, and it is a lot quieter at night. Some of this is wind noise because it tends to be a little bit breezier during the day, but we can definitely hear more coming from the road that's going right by Biscuit. You look at Norris is just quiet.
Yeah.
I mean, the acoustic energy you get Norris, it's like if you see a spike, it's probably something.
Right.
Whereas there's a constant background thing that's more prevalent during the day. And I think we see some moving acoustic sources. I haven't verified this yet, but I suspect they may be, and these are very, very occasional, helicopters coming into Old Faithful. There's a helibase there, and sometimes when they'll do medevacs, they fly out Old Faithful. So I've been there many times with helicopters have flown over, and you'd get a moving acoustic source with that. So a lot noisier, but a different frequency content, and one that we can usually filter out.
Right.
Pardon me.
Yeah, no, you're good. Yeah, that's a really good question she asked there. Let's see, Red Rover, is it useful to report the did you feel it on the earthquake site on USGS when apparently it's a small local incident? So how much help is that to the scientists for citizens to report that?
It can be incredibly helpful because there's a whole pardon me. Yeah. There's a whole intensity scale to earthquakes as well. Just because an earthquake may have a certain magnitude, as we were just talking about, doesn't mean that it wasn't impactful. And this is why, like a magnitude 5 in one place can be, not that noteworthy, whereas the same magnitude earthquake in another place might be devastating. Right. I mean, this earthquake in Afghanistan was a 6, right?
Yeah, 6.0, which, most places that's felt but not significant.
Yeah, I mean, it's felt and it may knock things off shelves, and part of that is, the context of, the infrastructure and so forth. But geology and location, depth, those things matter hugely. So yeah, even if it's a small event, putting out a did you feel it report is helpful, because the more people that do that, the more we might understand some more things about the characteristics of a certain region. Like, oh, hey, look at this. We're always getting did you feel it reports for small earthquakes from this area. Mm-hmm. So there's something about the geology of this area that is making the shaking feel stronger.
Yeah. Yeah, it's important
or
data.
Be more noticeable. Yeah, exactly.
Data for sure.
Exactly.
Okay. Quake Cat Utah wants to know, can a normal fault have strike slip dynamics such as the Wasatch Fault?
Yes, you can get mixed motion on these faults. In fact, most fault motion is mixed in some way. It's very, I don't know if it's very rare, but it's unusual to see like the textbook, normal fault that just does that. Usually there's a component of some shear on these faults. So rarely are they perfectly normal faults, perfectly strike slip. They're usually mostly one or the other, but there's often a component of shear on them, and sometimes they get super messily complex.
Yeah, they can be a little bit oblique. Yeah.
Yeah.
All right, Leanne Munoz, do you know of any interesting new research in geology or volcanology that leverages AI or machine learning in fun ways?
Yeah, I mean, this is sort of like the hot topic right now.
Yeah, this is the cusp of.
So the University of Utah is testing out an AI for locating earthquakes automatically, and it is locating more small events than the analysts have been able to do. And then the analysts go and they look at the pics, and they're pretty good. This is, there are not many places that are operationally deploying an AI location system. Mm-hmm. They still can't use it to get magnitudes. They're working on that part of it. But it looks like getting the locations. But it looks like for getting locations of very small events, AI probably is doing some interesting things in that regard. Right. It's also being applied to identifying deformation events. So, for example, we used to be like, we just didn't have a lot of data. Now there's thousands of GPS stations, and there's radar from satellite that are sending down terabytes of images almost a day. It's more we can keep up with. So AI approaches have been developed to basically look through archives of ground deformation data and then flagging things that thinks are deformation. And so now an analyst looking at a global catalog, instead of having to look at 10,000 images, can look at 50 that are flagged as like, I think there's something going on here. And maybe in the 50, 45 of them are atmospheric noise or something like that. Right. But the analyst can look at it and go, yeah, no, wait a minute, look at that. Right. And so now you're only looking at 50 images instead of 10,000. That's manageable.
Right.
It's also being used in looking at the microscope sections. Normally, a geologist would look at some of these thin sections of rocks and do counts and things. And a lot of that, more of that can be done by AI. Looking at deposit types. So geologists are starting to use it as well in interesting ways to better understand the deposits that they're mapping. So there's a lot of neat applications. It's definitely the cutting edge.
Right. Because it's got all the data of everything past, previous sort of known, and it's much better than we are at like aggregating that, finding the anomalies, finding the similarities, and then bring it to our attention.
Yeah, the challenge is in training these AIs. Right. And so you have to have really good training data sets. They're only as good as we teach them, basically. It's not like you just sort of turn this black box loose on a data set. You have to spend some time teaching it how to locate an earthquake. And so, for example, the earthquake location work that the University of Utah is doing, they found that if you get earthquakes, even small ones, in places that have had past earthquakes, the computer kind of knows, the AI knows, okay, I've seen this before.
Right.
If you get an earthquake in a totally random place, it can still confuse it. So
like novel earthquakes, yeah.
And then so it's still not a replacement for people, and it's not a perfect one size fits all solution. There are still these unicorn things that happen, some regularity, and the AI is not so reliable for those.
But it's better. It's improving efficiency, which is great.
Yes.
It's
absolutely. And it'll be especially valuable when we have these swarms of earthquakes where they're just happening rapid fire. Analysts can't keep up with that. And it's very difficult sometimes to separate out earthquakes when they're happening just right on top of each other.
Right.
Whereas an AI might be able to more efficiently get in there and dig out individual events.
See trends.
So for swarms, might really be pretty efficient.
Yeah, that's interesting. We'll have to see. Yeah, that's definitely something that'll evolve pretty quickly over the next months, years, that sort of.
Yeah, I feel like I'm going to wake up tomorrow and there's going to be some new. It's happening so fast.
Yeah. Okay. Well, I got 3 more for you. If you can hang in there just a couple minutes. So Jacques Swordfigure is there a way to monitor using a satellite, maybe stationary satellites? That's all the question says. So hopefully you got that.
That's an interesting question. So we do use geostationary satellites for thermal monitoring. They tend to not have the best resolution. So you're not getting down to like, a few meter pixel sizes with some of those satellites. They tend to be a bit bigger. So they're good at detecting hotspots that are, so if an eruption happens, we can see those. Some of the images, of the Tonga plume back in 2022 are from satellites like that. basically weather satellites. What has been kind of talked about in a theoretical sense was having a geostationary radar satellite. And that's a really interesting idea. The problem with the radar satellites now is they orbit the Earth. And so you only get a repeat once every X number of days. Typically it's 10, 12 days, depends on the system. Some systems occasionally will have a 1-day repeat. It varies. But if you had a geostationary radar satellite, you could get a repeat every, what do you want, right? It's just constantly looking at
it's constant data almost.
Yeah. So that has been discussed, and the kind of physics and the principles behind it have been played with, like back of the envelope sort of calculations. There's nothing that's planned, to my knowledge, in terms of a mission, but it seems viable. And if there was enough motivation for something like that, enough applications, we might be able to see sort of like a geostationary radar satellite that might eventually really help with kind of real-time monitoring of ground deformation.
Yeah, another kind of cutting edge thing. Okay, Kim Myers, here's kind of a fun personnel question. She studied geophysics at the University of Utah with Bob Smith, who did a lot of work at Yellowstone. She wants to know if he's still around.
Yes, he is. He's retired.
Yep.
And he spends a lot of his time living in Moose outside of the Tetons. And then in the winters, I think he's more often in Salt Lake. He checks in on us from time to time on our YVO calls, and he hangs out every time to time at University of Utah. So
he's lurking in the background.
Yeah, he's a giant in kind of Yellowstone geology, seismology. He established a lot of what is there today and being built upon, especially by folks from the University of Utah, but also USGS and other places.
Yeah, definitely one of the giants that you and others are kind of like standing on the shoulders of.
Absolutely.
Yeah. All right, last question, Mike. This is a fun one. Jake Grote wants to know, is Craters of the Moon, Idaho part of the same system as Yellowstone?
Okay. You could probably answer this better than I could, Shawn. So it's not directly connected. And this is something that I see come up from time to time, people saying, well, the magma system from Yellowstone stretches all the way to Boise, and that's not the case. However, there is a relation, right? So, the Snake River Plain, the Eastern Snake River Plain is the track of the Yellowstone hotspot. It went through there millions of years ago, but it created a situation that is conducive to volcanism now. What exists under, especially Craters of the Moon, but really the whole Snake River Plain is a volcanic province, is sort of this kind of sill, this zone of melt that's, I don't know, like 20, 25 kilometers deep or so.
Do we know that there's still magma down there, or would you just call it like hot rock or crystalline mush at this point?
Probably crystalline mush.
Okay.
But periodically, episodically, there are, injections from that, probably into that and then out of that, that will then feed eruptions. So a lot of that situation was facilitated by the passage of the Yellowstone hotspot. It is not sustained by the Yellowstone hotspot. Now the hotspot is out of the picture. There's not a continuous magmatic system that stretches all the way back into Idaho. The Yellowstone magmatic system is in Yellowstone. The record of that is preserved in the Snake River Plain, but because the area is still extending, it facilitates rise of basaltic melt and the generation of basaltic melt due to decompression. And part of that was sort of made possible by the passage of the hotspot.
Yeah.
So you're sort of dealing with like the tail end of the effects of the hotspot,
right?
But not a direct. So the Yellowstone hotspot is not directly feeding Craters of the Moon.
Yeah, I mean that's pretty much how I explain it too. That the Yellowstone, the passage of the over the hotspot, kind of set the stage.
Yeah.
Injected this basaltic magma, and then the basin and range extensional component kind of has sustained it longer. We don't know, probably it's going to erupt again. We don't know when, but
yeah.
And you guys actually monitor the Craters of the Moon area and the Snake River Plain, the Eastern Snake River Plain. So if we were to have people like, well, what would that look like? Well, I'm like, okay, earthquakes, ground deformation. Like, as soon as I start seeing swarms of earthquakes out near Arco, I'm going to get really excited. but we're not seeing that.
Yeah,
yet.
and I think one of the questions that we're still working on is what would the monitoring for such an eruption look like? There's some suggestion, and this isn't true universally, that these magmatic packets rise very quickly.
Like
possibly
quickly. Yeah, sorry, go ahead. You're about to tell us.
days.
Yeah.
You know,
Wow.
from depth, right? Maybe it takes long, but some of the material when it comes out, it doesn't show that much sign of sitting around at shallow levels, like in a magma chamber.
Right.
It may sit around at deeper
fast.
levels,
Yeah.
but yeah. So up it comes. It doesn't stall on the way there. So we haven't monitored an eruption like this in modern times.
Right.
We don't know, and very likely there is some variation from place to place and style, volcano to volcano, but it's possible that these things could rise pretty quickly. And
that's even more exciting to me.
I mean, I think about this in terms of the Four Corners as well. There's volcanic fields all throughout,
right?
Arizona, Utah, New Mexico, especially one area of Colorado, and the same thing may happen there. Now, fortunately, also in Idaho, the areas are pretty sparsely populated, so the odds
from a
of
hazard
impacting,
standpoint, not too big of a deal,
but it's going to degrade downwind air quality. It could put ash downwind, which may affect airports and air travel downwind. Lava flows could impact transportation corridors. The Zuni Bandera volcanic field in New Mexico, I think it's 3 times in the last 15,000 years, lava has crossed where I-40 is today. Right? So
that's significant,
Yeah, I mean, it may not kill anyone, but if I-40 is not usable for a long time, then that's pretty big. I mean, that would have an impact.
Right.
So I think the potential impacts of such an eruption, even if they wouldn't be like immediately and devastatingly as hazardous to human life as, say, an eruption of Mount St. Helens or one of the charismatic stratovolcanoes,
right? It
would still be pretty impactful.
Yeah, for sure.
And we need to know more about how those eruptions manifest. We don't have a great. We're working on that. It's not something that we know as much about compared to, say, how St. Helens or Hood or Shasta would erupt.
Yeah, for the craters ones, we think they're pretty short-lived, right? Like, they maybe go from, the magma rises quite quickly, like you say, then the eruption lasts days, weeks, maybe a few months at the most, and then, then it's over. But in that time, it can spread lava over a pretty big area. You could have, locally, explosive pyroclastic behavior.
And there's weird stuff out there too, like Big Southern Butte.
Yeah.
Right? I mean, that's like a huge rhyolite body.
Yeah.
There's a few of those things out there.
It's younger than your big eruption in Yellowstone. So it's, and there's
what's going on there?
I mean, we just explain it as just like, I mean, it's probably a simple explanation, but it's a little bit of that rhyolitic magma in the subsurface that's probably gas poor for the most part. Although Big Southern Butte did have some explosive phase. You can see some pumice and there's some tephra deposits there, but not a lot. It's mostly just oozing out this lava. But some of it's in storage. But I always wonder, like, well, what's driving that? What's initiating that? Why didn't that just stay underground and cool and crystallize? What actually initiated that coming out of the ground?
Yeah.
And I don't know. Like it's neat to think about. But you see, there's those are the obvious ones. And then if you go further back down the chain, just north of here, like 45 minutes on your way to Sun Valley, there's Wedge Butte. There's several of those rhyolite domes. A magic reservoir caldera that's like 3 million years old. So it's happening. It's happening at a time when it shouldn't be. The hotspot's in Island Park, and yet we're getting this sort of down track rhyolitic volcanism, some of which is explosive, that no one's really had a good explanation for that I've heard of. It's fascinating. It's awesome to think. Well, hey, Mike, this has been great. I appreciate you giving us time today. As always, our 4-time guest, Mike Poland of the USGS. We'll cross our fingers and hope for a 5th one sometime in the future. But yeah, we can maybe circle back later as we get into winter, and it's always fun to have a conversation with you. So thanks so much for your time today.
Yeah, thanks for having me. Good chat.
All right, well, we'll see you soon. Thanks, Mike. Take care.
See you later.
All right. All right, folks. So there we go. That was our conversation with Mike Poland. So he's always super awesome. I know we had a 3rd page of questions that I wasn't able to get to with him. So I do apologize for those that sent those. I'll try to keep that page around. Amanda Jo, maybe help me out remembering that. And I'm sure we'll circle back to Mike here in a few months or so, maybe after Christmas, sometime like that. and have him on again. He always does a great job. It's fun for me because it's just me sitting here, looking at him, having a conversation and discussing. I actually can't even see the live chat when it's happening. And I felt like I could just sit here and ask him questions and learn from him the whole time. But it's fun for us to learn together. I appreciate those that were able to help facilitate the discussion with their own questions. We had a lot of great questions from our viewers. Thanks as always to Susan Helmer and Mandy Joe on the live chat for taking care of folks there. Last couple of things, I guess, just kind of looking forward and moving forward. I turned off my webcam. Yeah, I'll just chime out. When I shut down the Zoom, it actually kind of kills the webcam there. So I'll just kind of chime in real quick here without my face showing up, and then we'll kind of let it go at that. But moving forward, look for a random road cut video this weekend. I did one with GeoGirl, so I met up with Rachel Phillips around the Yellowstone area. Well, we were actually in eastern Idaho, and got her to do a random road cut video with me. So look for that. That'll be kind of fun. And then what else? Just more of the same. Just kind of checking on some of these current events that are of interest to me. I'll get out in the field and do some more videos here in the next couple months as we roll into fall. But appreciate everyone who supports the channel. Hope you enjoyed this little experience and conversation with Mike Poland, and we'll see you next time.